This lesson is on vector fields, and a vector field is a function that assigns a vector to each point in space. So let's take a look at a fairly common example. What we're looking at here is a wind speed vector field. The direction and the size is located on this image. So you'll notice what we have. It appears as if there is some sort of rotation. My guess would be this might be indicative of a tornado or something to that effect. So we can see how these are used in real world to measure things like wind and current and such. So let's take a look at a fairly simple example. We will define one of these vector field functions as capital F of xy. That is the notation I typically like to use. And let's say it is negative y comma x, or if you prefer the other notation, negative y multiplied by the I vector, which of course is 1, 0, plus x multiplied by the j vector, which is 0, 1. So let's pick a collection of points and identify the vectors at those points. The point 0, 0 would have the vector negative y, negative 0, comma 0. So no visible vector there. But if I'm at the point 0, comma 1, what do we get? Negative y value, negative 1, comma 0. If we're at the point 1, 0, it'll give me negative y, 0, x is 1. So let's take a look at those vectors. So here is an xy plane. I am putting in this vector, which is negative 1, 0, and that occurs at the point 0, 1. So you could see where that vector is. And let's go ahead and add the vector 0, 1. Notice I have this vector here, 0, 1. And that occurs at the point 1, 0. And what does that look like? Now we have those two. So let's add a few more so we can get a feel for how this vector field is operating. So adding the vector 1, 0 at 0, negative 1, and the vector 0, negative 1 at negative 1, 0. What will those look like? So here is the vector 1, 0 at the point 0, negative 1. And here is the point 0, negative, excuse me, the vector 0, negative 1 at the point negative 1, 0. And you'll notice some sort of rotation that seems to be happening here. Now we can add a couple more vectors just to get a feel for what else might be happening. So at the point 1, 1, what do we have? We have negative y, negative 1, 1. At the point 1, 2, for example, negative y, negative 2, 1. So let's quickly add those vectors and see what they look like. So adding those two, we get this. Now, certainly, there's no way you're going to draw all of them. There's an infinite number of them. So we can actually use a tool to get a better feel for what this looks like. So let's do that. So coming back here to this app, I'm going to add a vector field. And they're giving me M, N, and P. M is in the I direction, N is in the J direction, P is in the K direction. We wanted negative YX. So let's put in negative YX. Scale vectors by dividing. I won't divide by anything. I'll just divide by 1 now so you can see that we have the same basic thing that we had before. Now that's a lot of vectors. If we can divide it by something, maybe by 4, you get a better idea of how this is behaving. And you can see the rotation nicely, rotating slowly on the inside, rotating more quickly as we move to the outside. Reminds me as a child being in an above ground pool, having all the children going in a circle, the velocity on the edges of that circular pool was very quick. The velocity towards the middle was actually fairly small. The speed was fairly small. So that's what a vector field is. That's what a vector field is. So let's take a look at another example. This time we have f of xy is x over the square root of x squared plus y squared, comma y over the square root of x squared plus y squared. Do you see what the size of each of those vectors will be? So think about that for a few seconds as we go back to the app to identify what that vector field looks like. So you'll notice I have x over the square root of x squared plus y squared in the m direction, y over the square root of x squared plus y squared in the n direction. And you may notice that these vectors are all the same size. They're all actually of size 1. Still difficult to see it here, so if I do a divisor, you can get a better idea of how this is behaving. And you can see, indeed, those are all the same size. They're all of length 1. And that's exploding out from the center out to infinity. So another interesting vector field. So here's a function, little f of xy is x squared y plus 3xy cubed. I'm curious what the gradient of little f is. So can we talk about what f sub x is? With respect to x, this would be 2xy plus 3y cubed. With respect to y, this would be x squared plus 9xy squared. So the gradient of little f is a vector. Recall the gradient is f sub x in the I slot in the x direction, f sub y in the j slot or the y direction. So what we get here for that vector is 2xy plus 3y cubed comma x squared plus 9xy squared. And I want you to recognize that this is a gradient field, right? In this case, what we say is we say this thing, big F of xy, the vector field written that way, 2xy plus 3y cubed comma x squared plus 9xy squared is a gradient field because it is the gradient of some function. So big F is a vector field. Big F is a gradient field. And what is little f? Little f kind of defined it, right? The gradient of little f equaled big F. And we say little f is its potential function. So little f of xy is the potential function of big F of xy, which is the gradient field. Make sure I'm clarifying my little f's and my big F. Little f is the potential function. Big F is the vector field. Let's take a quick look at that gradient field, see if it looks interesting. So moving to the app, I've got that plugged in there. The m part is 2xy plus 3y cubed. The n part is x squared plus 9xy squared. Very difficult to see when I'm dividing by 4. Let's divide by a bigger number like 20. Can we get a better feel for how this vector field is working? Maybe a little bit better. Let's even go to 40. And you get an idea where things are headed. Heading in this way, out that way, in this way, out that way for that vector field. That is a gradient field. And again, its potential function was little f of xy, which was x squared y plus 3xy cubed. This is going to be an important definition for us. If a vector field has a potential function, we say the vector field is conservative. Now, why the word conservative? Because vector fields are used to show situations where things like energy is conserved. So that's going to be an important idea. If we have a potential function like our last example, the vector field I gave you previously was a conservative vector field because there was a potential function whose gradient defined that vector field.